Good morning, and thank you for the opportunity to come and speak here about a passion of mine, which is cognitive computing. So I want to talk a little bit today about kind of the intersection of cognitive computing and the explosion of data that we see in the world around us. And I want to make the argument that at the core of making a city smarter and more sustainable, we have to get to deep insights that are not easily accessible. And the ability to get to these deep insights is driven by advances in computing that ultimately enable us to make future cities more sustainable and more energy conscious. So I'll try to cover a lot of ground in my talk today, but I realize we only have 10-15 minutes, so I'd be more than happy to continue conversations after the talk as well. So as a synopsis, what I want to talk about today is that we're at an extraordinary time in the history of civilization, the history of the world. And in particular, what's interesting about our time is that ever since the birth of the internet, we have had a tremendous explosion of technologies and information and data, all of which are driving huge advances in many fields of human endeavor, and in particular in areas that deeply impact us, such as our ability to live our life in a more fulfilling fashion. At the core of all this is that computing, which really began about 60, 70 years ago, has come to a point where there are exponential advances that are coming together. And the world around us is changing extraordinarily rapidly at this point in time. And what computing is really after, and why there are all these advances in computing, is that there is a lot of hidden knowledge that's present in the data that we're generating. Now, this is data that's being generated by all the sensors and the video cameras and the instruments that we are instrumenting our life with and our planet with. But it's also information that's coming from us, from things like social media, from Facebook, Twitter, YouTube, etc. All of these are basically nuggets of, they contain nuggets of knowledge and wisdom and insights that have to be mined. And the ability to mine at a broad level is really what I'm going to be talking about. And the nature of the information that's present and the similarity between various sources of information and the deep computing advances that are being made and that have to be made for us to truly mine and get value out of this. So let me talk a little bit about Moore's law, and in particular about the Moore's law applied to sensors. So at the core of the whole computing revolution, about 60, 70 years ago, we went from having, inventing the transistor, to having a few transistors on chip, to exponential increases in the number of transistors per chip. So at this point in time, the chips on your smartphones and on your computers have anywhere between 1 to 10 billion transistors each, right? But what's interesting is that we didn't actually limit the proliferation of transistors to semiconductor chips. We started putting them into other devices such as sensors. And so we have sensors now that went from having no computing or no intelligence to sensors that are deeply intelligent, that have tremendous numbers of transistors on them, and also sensors that were very difficult and very clunky and very remote to sensors everywhere. So we're at a point in time where we have huge numbers of sensors that are intelligent, that have a lot of computing in there, and that are driving a lot of data generation. So as a couple of examples, there are things like night vision and collision avoidance systems were actually very obscure a few years ago. Now, if you were to buy a reasonably high-end automobile, you have all these kinds of things that are coming in, and these things were actually very remote and they were not accessible to common people just about 4 or 5 years ago. Then there are things like MEMS-based accelerometers that are all over the place. They're in toys, in pico projectors, in solar powered systems, etc. So how is it that we went from sensors that were very remote, that didn't actually have a lot of intelligence, to sensors everywhere? At the core of this is basically the whole law of accelerating returns, which is very similar to the same law that actually drove progress in computing and in chip technologies. So what are all these sensors producing, and what's all the information that people like us are producing? Where is all this information going? So if I look at the kind of information that we're creating, it's primarily unstructured data. So that's at the core, that's the real difference in the world today. So about 5 to 15 years ago, most of the data that was present in the world was primarily structured. It was data that sat neatly in databases. It was easy to mine, easy for us to achieve insights from. And also the data was somewhat contained. And today we have a tremendous explosion of data driven primarily by both signal data. Video data is now about 50 to 60% of the entire traffic on the internet, and unstructured data generated by people, human generated, Twitters, blogs, etc. And so we call this at IBM ubiquitous and massively growing data. And the problem with this data is that the rate of change of data is nonlinear, which means it's growing much faster than we can mine information from. And so if you were to take one step, look at it a little bit deeper, what are the various problems with the data? First of all, in many cases, if we want to mine this data and get insights, we need to have sufficient relevant data that we can have trained our computing systems with. And a lot of times what happens, especially in video data, is that you're seeing new images for the first time, and it's very hard to train these neural network algorithms and machine learning algorithms to anticipate new information, patterns of change, patterns of information that are changing. So the lack of relevant data, the fact that data is changing very quickly, and the fact that it's growing very quickly, all of which contribute to the inability to extract new knowledge and the inability to get timely, continuous learning. So how do we solve this issue? The way to solve it really is to invent new computing paradigms. And these new computing paradigms stretch all the way from new chip technologies to new kinds of machine learning algorithms and the convergence of things like machine learning and natural language processing to drive brand new insights. So let me explain the nature of the problem in a little bit more detail. So let's look at signal data. A recent study by Cisco that's widely quoted, and I have a colleague from Cisco here, shows that there will be about 50 billion devices by the year 2020.